Hi everyone. In this video I will be discussing a couple of ways to identify potential heteroskedasticity when performing linear regression in SPSS. Now before we get started, I want to mention that underneath the video description you will find a link to the SPSS data file that I will be working from, so you can download the data to follow along. You will also find a link to a PowerPoint that provides additional details that you might find useful. So before we open up SPSS and begin analyzing data, let's first revisit the concepts of heteroskedasticity and homoscedasticity. So we'll begin with the assumption of homoscedasticity. So when you're performing linear regression, the assumption is that the variation in your residuals or prediction errors is constant across levels of your predictor variables. So the condition where you have constant variation in the residuals, that is referred to as homoscedasticity. When you have non-constant variation in the residuals, then you have a condition known as heteroskedasticity. And the reason why this is important is that when heteroskedasticity is present, this can produce biases in the standard errors, test statistics, and confidence intervals associated with your estimated regression parameters. So ultimately, this can lead to incorrect inferences regarding the nature of population parameters. Now in the figure below, we have a residuals plot. This is from a regression that I ran. And we have the studentized residuals that are plotted against the standardized fitted Y values. So in this plot we see that there is a fairly even spread of residuals across levels of the fitted Y. So there's no discernible pattern that's taking place in the residuals. The residuals look to be fairly randomly and evenly distributed. And this is the condition that we ideally would have when we are performing a linear regression. Now let's compare the situation we were just looking at with another situation where we have heteroskedasticity. So the plot on the right, this is actually one that we will see when we are working through the examples in this video. But the plot on the right has, we have heteroskedasticity being present. So as you're looking at this, you'll notice that as we move from left to right in the plot, you'll notice that the residuals exhibit different dispersions across levels of our fitted Y values. So you'll notice that on the lower end here we have much less spread or dispersion in the residuals, whereas when we were moving to higher values on the fitted Y's, we have much greater spread. So again, this is referred to as heteroskedasticity. This pattern right here, this is sort of the classic fan shape or funnel pattern. There is a little bit of a curvature in there which might signal some nonlinearity, but in general this is kind of what you would expect with this type of pattern, is just in certain regions, like in the low end on our fitted Y values, we have less dispersion, and as we move towards higher values we have greater dispersion. The funnel could also theoretically be reversed, where we have greater dispersion at lower fitted Y values and less dispersion at higher fitted Y values. So this is the classic funnel shape pattern or fan shape pattern. There are other patterns that could be evident. There's also a butterfly pattern that could sometimes become manifest. So there are different types of patterns. So the main thing to keep in mind is just that non-constant variation across levels of your predictors, and in this case this is across levels of our fitted Y values. So briefly, before we open up SPSS, let's consider our examples and our example data. So our example data is actually associated with this file right here. This is employee-data.save. This actually comes as an example file with SPSS, and I made some revisions to it for the purpose of this demonstration. So the file we're actually using is this one right here, and it can be downloaded at this link right here. And again, I'm going to include that link underneath the video description. So the data set contains employee data, so each row represents a given employee, and we have a number of variables reflecting different characteristics of employees. So what we're going to be doing is predicting the increase in employees' salary as a function of education level, amount of time their job, previous experience, and gender identification, which is coded 0 for identified male and 1 for identified female. So this diff variable that you see right here is just computed by taking the salary variable, current salary, and subtracting the salary the beginning salary right here. Our education variable is this one right here. We have job time. This is the amount of time at the job, previous experience, and then there's our gender ID variable, which is again coded 0 for identified male, 1 for identified as female. So I thought I would begin this demonstration by starting off with a simple regression, and then we would proceed to a multiple regression. So we're going to run a simple regression and examine the residuals for evidence of heteroskedasticity. So we're going to be running our model where we have diff as a dependent variable and education level as our predictor or independent variable. So to do this, we're going to go to Analyze, go to Regression and Linear, and now I'm going to move the diff variable to the dependent variable box and educational level to the independent variable box. Under the Statistics tab, I'm going to click on Confidence Intervals, Continue. Under Plots, I'll go ahead and request a residuals plot, so where we have the fitted y values. These are the standardized fitted y values. We're going to move that to the x-axis and studentized residuals to the y-axis. And we'll also click on standardized residuals plots. These are actually more useful with respect to examining the normality assumption. And just keep in mind that the normality assumption in the context of linear regression pertains to the residuals, not actually to the dependent variable y. Although outliers and non-normality on the dependent variable will certainly have an impact on the normality of the residuals. So we'll click on Continue, and then we'll click on Save, and we'll go ahead and request the unstandardized predicted values, unstandardized residuals, and studentized residuals right here. And we'll click Continue and then on OK to get our output. So as we're looking at our output, you'll notice that we have our model summary table. We have the R-square value being 0.339, so the predictor accounted for about 33.9% of the variation in the increase in salary variable diff. We see that the f-test is indicating statistical significance, so we would infer that the population R-square is greater than 0. Then we'll scroll down and we can look at our coefficients table, and you'll notice that we have our unstandardized coefficients for the intercept and for our predictor right here. And the next column we've got standard errors, and this is where that issue of heteroskedasticity can wreak havoc. So basically, if we have heteroskedasticity, that can lead to biases in the standard errors. And so keep in mind that when we are computing the t-value, the observed t-value from our data, the t-values are computed as a ratio of the regression slope to the standard errors. So if there's a bias in the standard errors, there will be a bias in our t-values, and then the p-values that are printed out as well will be incorrect. And we would also expect then that the confidence intervals would be incorrect as well. So that is a key reason why heteroskedasticity can be problematic when we are running our regression analysis, and why ultimately it can lead to incorrect inferences concerning our population coefficients. So let's go ahead and scroll down and we'll take a look at our standardized histogram of the regression standardized residuals. And looking at this, you can see what's produced is a normal curve overlay, but you'll notice that we have a pretty good positive skew in the data. It may not be easy to see on your screen, but you'll notice that we have some outliers here that are taking place. So we actually have a pretty good positive skew going on. When we look at our normal PP plot right here, we see that the residuals are not falling particularly close to the regression line. So that's also an indication that we have a violation of normality. So let's scroll down a little bit further and you can see that we have our residuals plot. So these are the studentized residuals plotted against the fitted y values, and these y values our fitted y values have been standardized. But as you look at this, you'll notice that we have much less dispersion in the residuals at lower fitted y values, whereas when we move towards higher values, we have our fan shape pattern, if you will, or funnel shape pattern. So visually, we have an indication here that we have heteroskedasticity taking place. Now, going back into our data set, we had requested some saved values. So you'll notice that we have the PRE_1. These are the unstandardized residuals from our regression model. And then we have, the PRE1 is the unstandardized fitted values or predicted values. The RES_1 are the unstandardized residuals for our model. So these values right here are computed by taking the scores on Y and subtracting the predicted values. And so again, basically it's Y minus predicted Y is equal to the residuals that we have right here. And then this column contains those standardized residuals. So the plot that we were just looking at essentially was a plot, again, of the residuals against the fitted Y values. We could also plot the residuals against our predictor variable. And so in this particular context, it's going to make less difference, but this is something that we would want to know about in the context of a multiple regression. So briefly, to do that, we're just going to go to Graphs, Legacy Dialogs, go down to Scatter Dot, click on Simple Scatter and Define, and we'll move our unstandardized residuals, or we could use the standardized, but I'm going to go ahead and stick with the unstandardized right here, move it to the y-axis, and move our independent variable education level over to the x-axis, and click on OK. And you'll notice that basically the plots are the same, and again, it doesn't really add a whole lot in this context because we only have a single predictor. I will say too, one of the benefits of using studentized residuals, if we go back here and run our analysis with the studentized residuals in here, one of the benefits is it sort of provides a way of identifying potential outliers. So if we use sort of a plus and minus 3 as a rough threshold for identifying potential outliers, as we're looking at the residuals plot right here, plus 3 would be falling right around at this point, a minus 3 would be falling actually down here. It's kind of off the plot, and you'll notice that we have a number of residuals that would exceed that threshold in terms of being potentially identifiable as an outlier. So that's one of the benefits of using the studentized residuals. Okay, one other approach that we can take in order to evaluate for the possibility of heteroskedasticity is to perform a significance test. And to do that, what we can do is go to Analyze General Linear Model and go to Univariate right here. And you might recognize this as the typical route when you're performing an analysis of variance of some sort, such as a one-way or factorial or ANOVA or an ANCOVA, but we can use this in order to perform heteroskedasticity tests. So to do this, we're going to move the diff variable to the dependent box, and we're going to move our independent variable education level down to this box for covariates. And next we'll click on options, and when this box opens up, we'll click on White's test. We can click on the modified Breusch-Pagan test, and these two tests can be very handy. Just really quickly, if we click under model right here, we have two options. We have use predicted values and use univariate model. We can just stick with the use predicted values for this model right here. And just so you know, basically the Breusch-Pagan test is useful for testing whether there is a linear functional relationship between your predictors in your model and the variance of the residual, or the variances of the residuals. Whereas White's test can pick up on potential nonlinearities between your predictors and the variances of your residuals. So that's why I've clicked on both of these. you'll notice that I've clicked modified Breusch-Pagan test as opposed to the Breusch-Pagan test. We could click on the original right here as well if we want to, but I'm just going to stick with the other one to keep things a little bit simpler, and also because that test is more robust to non-normality. So that's why I've selected that one. So we'll click on continue and then on OK to get our output. And so now we have two test results that are given. So we have, again, our modified Breusch-Pagan test for heteroskedasticity. We see that it's statistically significant. So this result right here is suggesting that we have heteroskedasticity of linear form. And then this test right here, again, it would pick up on potential nonlinear functional relationships between the predictors and your residuals. And so this is also statistically significant. You'll notice as we look at this that the basic model in this case, because we have our single predictor, we have education level, and then we have the education level squared. So it's essentially modeling a polynomial relationship between our predictor and the residuals, or the variances of the residuals, and that polynomial model being a quadratic model. Okay, so now let's transition to a multiple regression. So what I'm going to do is go back into the data set, and to keep things a little bit simpler, I'm going to remove these right here. And what we'll do is we're going to go back and we're going to run our regression, but this time we're going to include job time, previous experience, and gender ID alongside education level. So now what we'll do is go to Analyze Regression Linear, and we'll move our month since hire, that's the job time variable, previous experience, and then gender ID, we'll move that over as well. So we'll click on statistics here, and we'll leave our confidence interval where it was. Plots, we'll leave all of these options selected so that we can review those, and then we'll click on save right here, and we'll just maintain these options as well. So in this case, our predicted values, residuals, and studentized residuals that we generate and that will appear in the data file, all of those will reflect the current model. So we'll click on continue and then on OK now to take a look at our output. So you can see we have our R-square value, so right here it's 0.394. So basically the predictors are accounting for about 39.4% of the variation in our salary increase variable. The F-test is indicating statistical significance, so again we would infer that the population R-square is greater than 0. Once again, we have our unstandardized coefficients, our standard errors, etc. With our unstandardized coefficients, you can see that that education level right here and month since hire, both of those are actually positive and significant predictors of our income increase variable, whereas previous month's experience and gender ID, those were actually negative and significant predictors. But as I've noted before, the impact of heteroskedasticity will be on our standard errors, and that will affect our t-statistics and p-values and confidence intervals that are downstream, so to speak. So we'll go ahead and scroll down, and you can see once again with our standardized residuals, it looks like we still have outliers that are in our data set. So just kind of highlight those. These would be our potential outliers right here. And so we have definitely evidence of a violation of normality. The same is obviously evident with our PP plot right here. And then if we look at our residuals plot, this is the same fan shape pattern that I showed you earlier when I was contrasting homoscedasticity and heteroskedasticity. Once again, this is one type of pattern that can become evident and that would suggest heteroskedasticity in your residuals. There are other types, again, such as the butterfly shape pattern. So we can see clearly then that the dispersion of the residuals is much less at lower fitted Y values as opposed to when we move towards higher fitted Y values. Now, going back into our data set right here, we have, again, these are the predicted y's or the fitted y's. So, and then basically our residuals right here, these are the unstandardized residuals, which are computed by taking the diff variable and subtracting the predicted y values for those the diff variable, the conditional y's. So those are the residuals, and here are our studentized residuals that are shown in this column. Now, we looked at that residuals plot containing the fitted y values, but it's going to be really important that you also look at whether or not we have heteroskedasticity in relation to each of the predictors. So what we'll do is we're going to generate scatter plots that contain the residuals, and where we are plotting the residuals against each of the predictor variables. So to do that, we're going to follow the same steps that I showed you earlier. We're going to go back to Graphs, Legacy Dialogues, and we'll go down to Scatter Dot, Simple Scatter, and Define. And we're going to leave education level in there for this particular one, and we're going to use the studentized residuals. We'll click on OK, and as we're looking at this, we still have evidence of heteroskedasticity in relation to the educational level variable. So right there, we can see that educational level, the prediction errors, the variation of the prediction errors vary across education level. And it looks like that the prediction errors are lower at lower levels of education, whereas the variance of the errors are greater at higher levels of education. So we'll go back to Graphs and go down to Scatter Dot again, and in this time we will use our previous experience variable right here. So we'll move that to the x-axis and click on OK. And this is kind of tricky, but there might be some heteroskedasticity in here. It looks like there could be potential differential spread where we have maybe greater spread at lower levels of previous experience and maybe less spread at higher levels. So that's this particular graph right here. We'll move on now to the next graph, which will be involving our months since hire. So that's our job time variable. We'll click on OK. And there's not really any kind of suggestion in terms of heteroskedasticity. It does look like we have some residuals in there that would be outliers, but we don't. There's not really any kind of pattern in here that would suggest a violation of constant variance or homoscedasticity. So next we will go then to gender identification. And in this case, it looks like there might be differences in the variances between persons identified as male and female. So for the male group right here, we have much greater spread in terms of the residuals, whereas in the female group, or identified female group, we have considerably less spread or dispersion. Okay, so now let's go back and run the Breusch-Pagan and White's test. So we're going to go to Analyze, Compare Means again. Oh, excuse me, General Linear Model, Univariate. We'll go back, and now we're going to include our additional predictors in the covariate box. So I'm going to move the previous experience variable and months since hire variables over into this box. So we have 3 right there. We'll add the gender ID variable right here. Under options, as you can see, we still have White's test that's given. The Breusch-Pagan test, we could either stick with the predicted values or use a univariate model. I'm just going to go with the univariate model and then click on Continue and then on OK. And so now, as we're looking at our output, you'll see, once again, with our modified Breusch-Pagan test, we have statistical significance, and we also see it with White's test. So both of those, again, are indicating that we have the evidence of heteroskedasticity. And I do want to point out that if it were the case that, say one test was significant and the other one was not, we would still have evidence related to heteroskedasticity. Just keep in mind that the Breusch-Pagan test is designed to reflect sort of a linear functional relationship between the predictors and the variances of the residuals. And White's test is capturing, it basically is going to allow you to tap into possible nonlinear functional relationships. So it is possible that you could have differences between these tests. Also, White's test is incorporating a lot more predictors than the Breusch-Pagan test. You'll notice right here, the degrees of freedom are quite different between these. And that's because with White's test, as you're looking at it, as the model is involving each of the individual predictors, there's education, previous experience, job time, there's gender ID, and then you've got the square of those predictors. There's education squared plus education by previous experience, education by job time, education by gender ID. Then you've got previous experience squared and so forth. So you can see that there are a lot of predictors that are being added into this model. So it is possible that you can end up with differential results between these two tests. So what do you do if you have evidence of heteroskedasticity when you're performing a regression? There are a variety of different possible solutions that are available to you. One quick and easy solution is to run your regression and request heteroskedasticity consistent standard errors. And you can do that very easily, not through the regression route. You can't obtain that going through regression here, but you can get those standard errors by going back through our univariate route and running the model as a GLM, and then under options clicking on parameter estimates right here, and down below you'll see we've got parameter estimates with robust standard errors, and we've got HC3 that's given right here. So believe it or not, the parameter estimate selection is going to generate regression output. It's basically reparameterizing the GLM in the form of a linear regression, or parameterizing it in the form of a linear regression. And so the output is going to give you enough information for the overall R-square and F-test, and you'll also get the regression coefficients. And then down below, by making that selection, you can get the HC3 standard errors and then the corresponding adjustments to the t-values and confidence intervals. So if I click on continue and click on OK right here, when we look at our output, you'll see this may look familiar if you're used to running ANOVAs through this route. You'll first off see in this first line it says corrected model, and the F value and the P value that's given, these are the same as the F value and P value from the F test in your regression analysis. So the regression output, these values are exactly the same. You'll notice too that down here it says R squared is equal to 0.394, the adjusted R square 0.389. Both of those are going to be exactly the same as from your regression analysis. So if you were going through the regression menu. So we can scroll down a little bit further. You'll see that we have our table of parameter estimates that are given. And so again, this is essentially a regression parameterization. You've got your regression slopes, standard errors, t-values, significance, and confidence intervals that are given right here. All of these values are exactly the same as what we had previously when we ran our analysis using linear regression. So there aren't any differences there. But still, we have that problem with the standard errors potentially being biased. So to get around that problem and to interpret our significance levels, our significance tests, we can go down to this box here, and first off, the regression slopes are going to be exactly the same as they are in the box above, because the regression slope should not reflect any type of bias due to heteroskedasticity. That's not really our concern. Our concern is with the standard errors. So the standard errors that are given right here are adjusted for heteroskedasticity, and so by virtue of that, we can trust our t-test with the p-value that's given right here and the confidence interval. The confidence intervals that are provided in this portion of the table. So from that standpoint, we can interpret the regression parameters, or the estimated regression parameters, from the table below as opposed to the middle table. Okay, so that pretty well wraps up this discussion. Again, I encourage you to download a copy of the PowerPoint that I referenced earlier in the paper. It does provide a little bit more detail than I'm really that I've gone through in this video presentation. So I thank you for watching.